In this video, we'll talk about consequences of the proposition that we proved in the previous video. So for the first one, let's let K be a subgroup of G and little g an element of G. Then if we conjugate the subgroup G by this element little g, sorry, if we conjugate this subgroup K by this element little g, we get something that is a subgroup that is isomorphic to K. So one thing this says is conjugate subgroups are isomorphic to each other. And one thing that implies is that conjugate subgroups and conjugate elements have to have the same order. So what's the proof? In this proposition from last time, how did it work? We started with a group G and a normal subgroup H, and we had G act on H by conjugation. So let's just take H equal to G. So now phi G is an automorphism of G. So you apply that automorphism to a subgroup K, and you get another subgroup K. Sorry, you get another subgroup that is isomorphic to K. OK, what else is true? Let's take H to be a subgroup of, let me say G prime, and it'll be clear in a minute why I want to use a different letter. Then the normalizer of H in G prime mod the centralizer of H in G prime is isomorphic to a subgroup of aught H. And G mod the center of G is isomorphic to a subgroup of aught G. So for the first part, in proposition 13 from last time, let's take the group G to be whatever the normalizer in G prime of H is. So this is why I want to use a different letter, G prime. I don't want to say take G to be equal to the normalizer of H in G, because it's a different group. So what I'm saying is you start with any subgroup of a group. You take its normalizer. And now that normalizer is also a subgroup. And the important thing is that your original group H is a normal subgroup inside its own normalizer. So now what does the proposition say? It says the normalizer mod the centralizer is isomorphic to a subgroup of aught H. Right? So H is normal in its normalizer. The centralizer of H in the normalizer just is the centralizer in the whole group. OK, and for the second part, we're going to take our subgroup H to be our whole group G in this proposition. And now what is the centralizer of G in itself? That is the definition of the center. So what the proposition now says is G mod the center is isomorphic to a subgroup of aught G. OK, so we'll see a bunch more applications. But I want to define something first. So we've seen that conjugation by G gives an automorphism of G. So it gives a permutation of the elements of G that has some structure to it. This kind of automorphism, one that comes from conjugation by an element, is called an inner automorphism. And we have seen that this set of inner automorphisms gives a subgroup of aught G. So we're going to use in G to denote this subgroup. And we've seen right here that this group of inner automorphisms is isomorphic to G mod the center of G. So there are all different kinds of questions you could ask. For particular examples, what is the whole group aught G? And then what is this subgroup of inner automorphisms? So I'll pause and erase, and then we'll talk about some of those questions. Now that we have this definition of the subgroup of inner automorphisms of aught G, we can ask, when is this subgroup equal to the whole group? So when are all of the automorphisms inner automorphisms? When do they all come from conjugation? So the answer is clearly not always. The set of inner automorphisms of G is trivial if and only if G is abelian. So why is that? Because it's isomorphic to G mod the center of G. So if the center of G is the whole group, then the set of inner automorphisms is trivial. Right? If you think about the map that takes x to g inverse, if your group is abelian, that's just sending x to x. All right, so let's think about some more interesting examples. Let's take the center of the dihedral group of order 8 that's generated by r squared, so this 180-degree rotation. So what does a group of inner automorphisms look like? Well, it's G mod the center, which is D8 mod this subgroup, which is isomorphic to Z mod 2Z cross Z mod 2Z. So what about the whole group of automorphisms? So Dummit and Foote work out a bunch of groups of automorphisms in the exercises. So exercises 3 and 5 together in section 4.4 show that the automorphism group of D8 is isomorphic to D8. So that means that the group of inner automorphisms is not the whole group, that there are some automorphisms of D8 that don't come from conjugating by an element. So what about the quaternion group of order 8? So the center there is the cyclic subgroup generated by -1. So the group of inner automorphisms is isomorphic to Q8 mod this center, which is isomorphic to Z mod 2Z cross Z mod 2Z. Same kind of thing. So what is the whole group of automorphisms? Exercise 4 in section 4.4 plus something much later. So this statement is more difficult to prove. Exercise 5 in section 6.3. These two together show that the automorphism group of Q8 is isomorphic to S4, the symmetric group on 4 elements. So what does that mean? There are a lot more automorphisms of Q8 that don't come from conjugating by an element. So what about symmetric groups? The center of Sn is trivial whenever n is at least 3. So the group of inner automorphisms of Sn is isomorphic to Sn for n at least 3. So exercises 18 and 19 in section 4.4, and then again something much later, exercise 10 in section 6.3, show that the group of inner automorphisms of Sn is the full automorphism group when n is at least 3, except when n equals 6. When n equals 6, there's an automorphism that does not come from conjugating by an element. So the group of inner automorphisms actually has index 2 in the full automorphism group. So these exercises are not so easy. Often computing the full automorphism group of a group is really quite tricky, but we always have this subgroup of inner automorphisms, the ones that come from conjugation, that we can really get our hands on. So the next thing I want to do is talk about an example that we've actually already seen in the homework, that the automorphism group of Z mod NZ as a group under addition is isomorphic to Z mod NZ star. So this is the subgroup, this is the group of elements of Z mod NZ that have multiplicative inverses. This is a group under multiplication. So I'm going to pause and erase, and I'll say something about the proof here. But what is this showing? Well, Z mod NZ is abelian, so the group of inner automorphisms is trivial, but it can still have a lot of automorphisms. They just don't come from conjugating by an element. Let's say a little more about this proposition about automorphisms of Z mod NZ. So first I want to give a definition. Let's say phi of n is the number of numbers, integers, between 1 and n. So integers I, where the GCD of I and n is 1. So it's a number of things less than or equal to n that are relatively prime to it. Why am I bringing this up now? Because Z mod NZ star is a finite abelian group of order equal to phi of n. It's a group under multiplication. That's easy to check. And the size is exactly what you need for an element to have a multiplicative inverse. That an element in Z mod NZ has a multiplicative inverse exactly when its GCD with n is equal to 1. OK, so let me point out that this proposition was already on homework 1 in some form. It's basically exercise 26 of section 2.3. But now we have a little bit different language at our disposal. So I'll still say something about the proof. All right, so a big idea is that a homomorphism is determined by where it sends a generating set. That if I give you a generating set for a group G, and I tell you where a homomorphism phi sends all of those generators, then you automatically know where it sends any element of G. In particular, in this case, where G is a cyclic group, if it's generated by X, then any homomorphism phi from G to some other group H is determined by where it sends the generator X. If you think about what this is saying, what is phi of X squared? It's phi of X times phi of X. So if you know phi of X, you know phi of X squared. But if everything is some power of X, then if I tell you phi of X, I'm telling you phi of X to the n for any n, and that the set of all X to the n, that is the whole set G, the whole group. We've seen earlier that an automorphism has to take an element of order n to an element of order n. That's something we proved a long time ago about an isomorphism between any two groups sends elements of order n to elements of order n. OK, so now let's look at this function psi a that's going to send z mod nz to z mod nz. And it's going to be determined by saying that psi a of 1 is equal to a. So there is a homomorphism such that psi a of 1 equals a. And that's this function psi a. So we're going to say it's a homomorphism. It's the one that's determined by sending 1 to a. And it's not difficult to check. When is this homomorphism an automorphism? It's exactly when the GCD of a and n is 1, when this element a also has order n, just like 1 does. And now you can check that this function psi that sends an automorphism of z mod nz to an element of z mod nz star, given by taking this psi a and sending it to the element a, or a mod n in z mod nz star, that this is an isomorphism. So in order for this function here to make sense, we need it to be the case that every automorphism is one of these psi a's. Neither one of these pieces is difficult, but there are some details to write down and check, or you can look them up in Dummit and Foote. So in the next video, we'll see a few more applications of this material about automorphisms that we've seen so far.